Hi, I decided we'll talk a little bit more about the topology of the spectrum of a ring. So let's see this lemma today. So let's take a ring A, and the statement is quite short, namely, oops, not A, spec A. Then the spectrum of the ring is quasi-compact. So that meaning that any open cover of the spectrum admits a finite subcover. Okay, so let's prove it. And of course, spec A is endowed with the Zariski topology. So let X equal to spectrum, so that's our topological space. And let's take an open cover of X. And well, now we have, so that's the open cover, and then we can write it by as complements of closed sets, so X without V of Mi for some subsets of A. And well, that's now we use the following rule, namely that this is just the complement of the intersections of the V of Mi's. Now we use properties of the Zariski topology, so we get the empty set as the union of these V of Mi's, which is V of this union. And what we're gonna show is that 1 is in the ideal generated by these Mi's. So we'll see in a minute why that's what we want to prove, but let's first prove it. So if not, then we have that this idea is in some maximal idea. So maximal ideal M, and then we use so also an easy property of this V of M is that if we have here on the left hand side, so we have one set being a subset of the other in the ring, then if we apply V to it, then this gets reversed. So we get that V of M is a subset of this V of the union, which is the empty set. So we've seen this here. And also we know that M is in V of M. Why is that? So M is a maximal ideal, so let me write the definition. So that's the prime ideals such that M is a subset of, let me see, the prime ideals such that M is a subset of P. That's right. So that's the definition. So we get M is maximal, so it's prime, so it's in here. So that's a contradiction. But now let me mention some further points. So also from this thing here, So that's an easy lemma or exercise. So you can do it as an exercise that the closed points in the spectrum of a ring, whereby what do I mean by closed points? I mean that if we consider the set X, that the set is closed. And this also, that's actually a good thing, so to remark that. So that being closed for all points would be equivalent to the T1 axiom, but spectrum of a ring is not T1, but it's T0. So that's maybe also an important remark. But or in general, it's not T1. It can be T1, but in general, it's not. And so that's some further remark about the topology of the spectrum of a ring. But let's go on with the proof now. So now we have a contradiction if one is not in here. So if one is not in this ideal, so we get one is in this ideal. So we get that we can write 1 as some AI, let's say A1 FI1 plus AN FIN, so with AI in A and FIJ in MIJ for some J in, for some J, let's just say, and also for some N positive integer. Okay, that's that, and oh well, yeah. Okay, and what we see now is that we can write now V of this finite union. So I should put J as a subindex of I, and that's the same as V of the ideal generated. So we could have started with that right away, but doesn't matter. And here we have 1 inside here, so we get that this is V of A, which is the empty set. And now taking complements again, we get that the union from J equals 1 to N Uij. So these Ui's were what we started with, and then we looked at the complements of these Ui's, and then we get that this is the spectrum of A, what we wanted to prove. So it's quasi-compact. Okay, that's it for today. I don't want to say too much what we'll do next time, because maybe I'll change my mind. But I think what we'll do next time is we'll look at closer at closed sets and irreducible sets, and maybe also again on the point I mentioned before, so closed points, but mainly probably closed sets and how they are related to ideals and or radical ideals, and then how irreducible closed sets are related to prime ideals and stuff like that. Okay, that's it. Have a good time and bye.